A Java synchronized block is a block of Java code which can only be executed by one thread at a time. Synchronized blocks are marked using the synchronized keyword in Java. In the class here on the left, you can see how I have used the synchronized keyword to declare two methods synchronized. And that is the setObject method here. You can see I've used the synchronized keyword here, and the getObject method here. Declaring an instance method synchronized means that only one thread can execute that method at a time on a given instance of that class. Now in the case here where we have two synchronized methods, it also means that only one thread can execute either this method or that method because both of them are synchronized. If you do not want to declare a complete method synchronized, you can also just create a synchronized block inside of a method. And I have two examples here in the setObj method and the getObj method here. As you can see, I have declared two synchronized blocks inside of each of these methods. A synchronized block can also only be executed by one thread at a time. And that means that this synchronized block here and this synchronized block here can only be executed by one thread at a time. Notice the object that is specified inside the parentheses of these two synchronized blocks here. This is called a monitor object, and the monitor object is the object on which these methods or these blocks here are synchronized. And if you look at the methods up here, they are declared synchronized, and that is the same as synchronizing them on this monitor object. So that means that all of these synchronized blocks here, the two methods up here and the two synchronized blocks here, are synchronized on the same monitor object, which is this instance. The effect of synchronizing the two methods setObject and getObject and the two synchronized blocks inside of setObj and getObj on the same monitor object is illustrated here on the right. In this example, we have a single synchronized exchanger instance which is shared between two threads. Thread 1 regularly calls setObject or setObj. It doesn't really matter which of these two methods is called because they do the same thing. And because all the code inside of setObj is located within a synchronized block, which is synchronized on this object, the synchronized exchanger instance as monitor object, the effect of calling any of these two methods is the same. Thread 2 calls getObject and getObj on a regular basis, and again, it doesn't really matter which of these two methods is called because the synchronized semantics of these two methods is the same. Because setObject and getObject and the synchronized blocks inside of setObj and getObj are all synchronized on the same monitor object, the instance of the synchronized exchanger class, that means that only one thread can enter any of these synchronized blocks at a time. So if thread 1 is currently executing inside of setObject, then thread 2 cannot enter getObject or the synchronized block inside of getObj at the same time. If instead thread 1 and thread 2 each had their own synchronized exchanger object, which they were calling setObject and getObject on, then the synchronized methods and synchronized blocks inside of each of these instances would be synchronized on the instance itself, meaning that when thread 1 calls setObject in this instance here, that only blocks other threads from calling any other of these methods on this instance, not on this instance. And in the same way, when thread 2 calls any of these getObject or getObj methods over here, that only blocks other threads from calling synchronized methods or entering synchronized blocks which are synchronized on this instance here. So the monitor object of the synchronized blocks matter To recap, let's have a look at the code over here on the left again. The two methods here are instance methods because they're not declared static. So that means that these two methods here belong to the instance. So any synchronized exchanger instance they will belong to, and you can call them on that instance. Because the methods are declared synchronized, that means they're synchronized on the synchronized exchanger instance. That is the monitor object these two synchronized methods use to guard access to these methods for threads. And that is similar to what we have done down here, where the synchronized block uses this as a monitor object, and also here. So that has the same effect. Synchronized instance methods are always synchronized on the instance method belongs to. But synchronized blocks can be synchronized on any Java object you want to use as monitor object. And I will show you examples of that later on. Let's just see an example of using the static synchronized exchanger here and having a thread 1 called setObject and a thread 2 called getObject. And I have an example here on the left. Now, as you can see, first I create a synchronized exchanger instance here. Then I create the first thread, which loops. It's given a runnable, and this runnable loops 1000 times. And for each iteration in the loop, it calls setObject with the string version of I. So it concatenates the empty string with I and sets that on the exchanger. Then we have thread 2 down here, which is also given a runnable, and this runnable also loops 1000 times, and it prints out whatever is returned from getObject on the exchanger instance here. And then finally, thread 1 and thread 2 are started. And let's run this example and see what is printed out. As you can see, we get a lot of prints outs from the second thread. Starts with a lot of nulls, and that is because it calls getObject before thread 1 has called setObject the first time, and this has to do with thread scheduling. So there's no guarantee about the exact order in which thread 1 and thread 2 gets access to the exchanger. They just cannot get access at the same time. But as you can see, thread 2 gets access a lot of times before thread 1 has even called setObject even once. But as you can see here, all of a sudden thread 1 gets access, right? And it starts calling setObject, and you can see that it reaches to call it 192 times before thread 2 gets a chance to come back and get the object, right? And then you see 7 times, no, actually more, it's more than 7. This is 13 times before getObject is called the second time, and then another 8 times, and as you can see, there are some gaps here, right? So that means that now thread 1 gets to call exchanger multiple times before thread 2 gets a chance to call getObject again. And then you can see it ends up here at 999, and that is the last value that thread 1 sets because it runs until I is less than 1000. So that is how it looks when two threads are sharing a synchronized exchanger here and calling setObject and getObject. You can also use the synchronized keyword with static methods and create synchronized blocks inside of static methods. And here on the left, I have created an example of the synchronized exchanger in a static version. First of all, you can see that the object variable up here is now static, and the method setObject and getObject and setObj and getObj, they are all declared static. A static synchronized method uses the class object of the class the method belongs to as monitor object. So that means that instead of using the instance of the class, as is the case with instance methods, it uses the class object. And that is because static methods do not belong to any instance. They belong to the class. And you can see down here in the setObj and the getObj methods that I have used the static synchronized exchanger.class as monitor object for these two synchronized blocks, and that has the same effect as declaring the whole method up here synchronized. Just to recap, let me show you here in the diagram on the right how that works. We have one thread here. Imagine you have one thread here calling setObject or setObj. It doesn't really matter in this case. And you have another thread calling getObject or getObj. And since these are static methods, and this is a static variable, right? Otherwise we couldn't access it from inside of static methods. But since these are static methods, only one thread in total can call any of the methods that are synchronized on the static synchronized exchanger class as monitor object. So when thread 1 calls setObj, thread 2 has to wait. When thread 2 is calling one of these methods, thread 1 has to wait. It is also possible for a class to contain both static and instance methods, non-static methods, which are synchronized. And I have created an example here on the left. You can see that the class mixed synchronization here contains a static variable and a static synchronized method which can set a value for this static variable. And then we have here a field, an instance field, and we have a synchronized instance method which can set a value for this field. And I've left out the getter methods just to keep the example simple. Even though these methods belong to the same class, the two methods are not synchronized on the same monitor object. This static synchronized method here is synchronized on the mixed synchronization class object, whereas the instance method down here is synchronized on whatever instance of mixed synchronization that the method is called on. This difference in monitor object means that you can have one thread calling set static obj at the same time as an instance method here is called on an instance of mixed synchronization by another thread. However, if two threads were to attempt calling set static obj at the same time, of course they would be blocked because they would try to enter the same synchronized block, which is synchronized on the same monitor object. Similarly, if two threads were to call set instance object here on the same instance of mixed synchronization, then they too would block each other out. Whereas if two threads were calling set instance obj on two different instances, well, then these two methods would be synchronized on two different instances of mixed synchronization. They would be using two different monitor objects, and thus the two threads would be able to call these two methods on different instances at the same time. It is actually possible to use different monitor objects for different synchronized blocks, even within the same class, and I've created an example here. In this class, I have created two monitor objects. These are just object instances. It could be any type of object, but right now I've just used object for simplicity. Then I have created two counters here, two counter fields, and then an inCounter1 method, which has a synchronized block, which is synchronized on monitor 1 on this object instance up here. And inside of that, we increment the counter1 variable. Inside inCounter2, we have a synchronized block, which is synchronized on the second of these monitor objects, monitor 2. And inside of this synchronized block, we increment counter2. Because these two blocks use different monitor objects, these two synchronized blocks, they will not mutually exclude threads from entering them. So that means that we can have one thread calling inCounter1 at the same time as another thread can call inCounter2 on the same instance of multiple monitor objects. And of course, if you had different instances, then of course they would also internally be using different monitor objects, and so they wouldn't block at all. However, on the same instance, only one thread can enter this synchronized block here, and only one thread can enter this synchronized block here at a time. It is even possible to share monitor objects between different instances of the same class, or even between instances of different classes. And I've shown you a simple example here in this class here, shared monitor object class. As you can see, it has a object monitor variable here, and that variable gets set in the constructor here, right? So when you create a shared monitor object instance, you pass whatever object you want to use as monitor, and we set that monitor into this monitor field. And you can see down here that in the inc counter method, that the synchronized block here is synchronized on the monitor object passed in here into the constructor and set into the field. Now, one thing to be aware of is that a monitor object cannot be null. It must not be null. If it is null, then you will get a null pointer exception when you try to enter this synchronized block here that is synchronized on that monitor object. So that is why I have inserted this if statement here that checks if the monitor is null, then we throw an exception. Let me quickly show you an example of how to use these shared monitor object and how to pass a monitor object to the instances of shared monitor object. Here's a simple example here. I create an object calling it the variable monitor1, and you can see I create two shared monitor objects instances which will have monitor1 passed as monitor object to their constructors. That means that the synchronized blocks inside of inc counter inside of these two instances will actually synchronize on the same monitor object, and thus calls from different threads to either SMO1 inc counter or SMO2 inc counter will actually block for each other, right? Because they use now the same monitor object. The synchronized blocks inside here will act as if this was kind of the same instance, but it's not. It's because the monitor object is the same for the synchronized blocks. However, down here in this last example here, we create a separate new monitor object, and this shared monitor object here uses this monitor object to synchronize on, and that means that for SMO3, the inc counter calls, if a thread calls the inc counter call here, it will not block other threads from calling inc counter on SMO1 and 2, because these two instances here use the same monitor object for the synchronized block inside, and this instance here uses a different monitor object for the synchronized block inside, as you can see here, right? The monitor object is taken as parameter to the constructor, and then the inc counter synchronizes on that object. Here's a different way to illustrate what is going on in the previous example. Imagine the blue boxes here are objects, and the red boxes here are synchronized blocks within these objects, and these red circles here are monitor objects. Then we have two objects with synchronized blocks inside, which are synchronized on a shared monitor object. And we have a third object here with its own synchronized block, which is synchronized on its own monitor object. Now, if a thread calls this object here, enters this synchronized block, then it will be, because it's sharing the monitor object with this synchronized block, it will block threads both from entering this synchronized block and also this synchronized block. However, a thread could easily call this object here, this synchronized block could easily enter here, because it is synchronized on a different monitor object, right? So of course you cannot have two threads entering this synchronized block, but you could have one thread entering this synchronized block and another thread entering either of these ones, not both of them, one of them. Sharing monitor objects between different instances is an advanced technique, and you can create some very interesting and very advanced synchronization mechanisms across various classes and instances of the same class or instances of different classes. However, a word of caution: once you start sharing monitor objects between different instances and even between different classes, it becomes a lot harder to reason about whether your final solution actually synchronizes correctly as intended. Just one final comment about monitor objects, and that is there are some classes you should never use as monitor objects. For instance, you should not use strings. For instance, if you did like this, like this, the problem is that you don't know how the Java compiler will optimize this behind the scenes. You don't know if these two strings here will actually be different string instances, or if the Java compiler behind the scenes will optimize this to be the exact same string instance. So in general, using string constants as monitor objects is a really bad idea. It's to stay on the safe side, use any object which is not a string, which is not one of the primitive wrapper types like integer or long or whatever. Just stick to using objects or instances of your own classes. It is actually also possible to have a synchronized block within a Lambda expression, a Java Lambda expression. And if you're new to Java Lambda expressions, check out the description below this video and you will find a link to my Java Lambda expression tutorials. In this example here, in this synchronized Lambda class, we have a single private static field object. We have a static setObject method, which is also synchronized here, as you can see. And then we have a static consumeObject method, which takes a consumer as parameter. This method is not synchronized, so for this to synchronize properly with the setObject up here method, the Lambda expression would have to provide synchronization. Now let's have a look at how calling this method, consumeObject method, looks in practice, right? So we call consumeObject, it's a static method, and we pass a Lambda expression here as parameter to consumeObject. Now, as you can see, this Lambda expression inside the body has a synchronized block, and it's synchronized on the class object of this class. Now, that is done to make sure that the Lambda expression here, the synchronized block here, will synchronize on the same object, the same monitor object that this synchronized method up here is synchronized on. Because this is a static synchronized method, it will also synchronize on the class object for the synchronized Lambda class. And yeah, consumeObject will call accept, and when that happens, this method here gets called, this Lambda expression gets called, and the whatever thread calls it will enter this synchronized block and print out the value of the object. Now down here you can see that it is possible to use a different synchronizer, a different monitor object than synchronized lambda.class. However, if you do so, setObject and consumeObject no longer synchronizes on the same monitor object, and you will not have an effective blocking of between the blocks. So a thread calling setObject will not block for threads calling consumeObject, because the synchronized block here uses a different monitor object. Now, since Lambda expressions do not belong to any object instance, you cannot use this as a monitor object, because there is no this object in the context of a Java Lambda expression, but any other instance you can get a hold of that you can access from within the Lambda expression can be used as a monitor object. Just make sure that whatever object you choose makes sense. So in this case, using string.class did not make sense, right? It was just an example. Whereas synchronized lambda.class does make sense because it makes consume object with this lambda expression synchronized on the same object as the setObject method. Java synchronized blocks are reentrant, and to explain what that means, have a look at this example here. This class has two methods, both of which are synchronized. And that means that the synchronized blocks that these methods are making up are synchronized on the instance of the reentrance on which these methods are called. So look at this. In case a thread calls this inc and get method, then inc and get calls to inc, which is also synchronized. However, since the two methods are synchronized on the same monitor object, and it is the same thread that calls both of these methods, then this second synchronized block will not block the thread calling it from inside the first synchronized block. And that is what reentrant means. It means that a thread that already holds the lock on the monitor object a given synchronized block is synchronized on, is allowed to enter a new synchronized block which is synchronized on the same monitor object. And that is what is going on here, right? First, we take the thread that calls inc and get, takes the lock on the monitor object that this method is synchronized on, which is the instance that it is called on, the method is called on. And then when inc is called, the Java virtual machine here detects that, oh, it's the same monitor object that this block is synchronized on, and it's this thread that calls it already holds that lock on that monitor object, so it is allowed into this method. So it is said to be reentrant. Java synchronized blocks affect the visibility of changes to variables that are visible to multiple threads. The way synchronized blocks affect the visibility of changes to variables that are visible across different threads is also sometimes referred to as the Java synchronized visibility guarantee. To illustrate the Java synchronized visibility guarantees, I have created this diagram here, as well as this very simple example class here. As you can see, the example class contains a single counter variable here, count, and an inc method with a synchronized block inside, which increments the count variable, and a get method, which also contains a synchronized block, which returns the value of the count variable. Imagine too that we have a single instance of the sync counter stored in main memory, and that we have two threads, each running on separate CPUs, accessing this shared sync counter instance. When thread 1 calls the inc method on the shared sync counter instance stored in main memory in here, what happens is that the count variable is read from main memory through the cache into the CPU registers here. In here, the count variable is incremented, and then it is written back to main memory. More specifically, what happens is that when thread 1 enters this synchronized block, all variables that are visible to thread 1 will be synchronized from main memory, means they will be read in from main memory. And that means that if the thread had any cached values here of that variable, then they will be overwritten with a fresh value from main memory. So in this case, the count variable here, the field, is visible, so that will be read from main memory through the cache into the local CPU registers. When the thread exits the synchronized block again, all variables that are visible to the thread at this point will be synchronized back to main memory, means they will be written back to main memory. So any old value stored here in memory will be overwritten with the latest value of the variable that is visible to the thread. So in this case, the count variable is visible to the thread, and so the count variable will get written back through the cache to the main memory again. The same happens when thread 2 calls the inc method. It enters the synchronized block, reads a fresh value of the count variable into its local cache and into its CPU registers, increments the count variable, and writes the value back to main memory. If we remove the synchronized block around the operation that increments the count variable, what would happen is that there would be no guarantee about when thread 1 refreshes the value of the count variable from main memory, nor would there be any guarantee about when it writes the count variable back to main memory. And the same would be true over here, and thus you could have a thread 1 read the value 0 in here, increment the count variable, but keep it locally cached here and never commit it back to main memory. And when thread 2 tries to call inc as well, it will also read the value 0 into its CPU, and then it would increment the value, and then maybe it would write it back, maybe it would just keep it cached here. Sometimes the write would go back to main memory, but sometimes not. And that means that a lot of the increments done by thread 1 would not be visible to thread 2, and a lot of the increments made by thread 2 would not be visible to thread 1. So if each of these threads were to execute inc 10 times each, the result could be anything from 10, the final result could be anything from 10 to 20. Because they would overwrite each other's updates, right? You could have this thread here increment count to 10, and then at that point write the value back to main memory, and you could have thread 2 do the same thing without ever seeing any of the updates from thread 1, and so the final result would be 10 when it should have been 20. With the synchronized blocks in place, you are guaranteed that, first of all, that the variables are always read in from main memory when the thread enters the synchronized block, and that whatever changes have been made are written back to main memory when the thread exits the synchronized block. And since the synchronized block also makes sure that only one thread at a time can enter the synchronized block, that means that you cannot have two variables reading count at the same time, incremented, and then write the value back on top of each other. Only one of the threads gets to increment the variable at a time, and thus none of the increments will get lost. Let me quickly show you the difference between having a counter which is not synchronized and one that is, and how that affects visibility. Look at this counter here. Yes, it's called sync counter, but the count method here, the inc count method and the get count method, they are not actually synchronized at all. Now, in this example, you can see I create a single sync counter, and then I create one thread here, which will loop 1,000,000 times and call inc count, and then print out whatever the final count is, and another thread that does exactly the same thing. And because they use the same counter instance, they both reference the counter instance here, well, then the total result should be 2,000,000, right? Whatever thread finishes first will not see, of course, a total of 2,000,000, but the last thread that finishes should see the result 2,000,000, right? Because each of them have counted 1,000,000 and incremented the count in the counter for every iteration in the for loop. And when we run this code, you can see that the second thread here only gets to 1.8 million, 1.9 million or so, not even the same number every time. Now let's see what happens when we make these methods synchronized. Synchronized void here and synchronized down here. Now, first of all, only one method or one thread can call the int count method at a time, which means that they cannot copy the same value. Two threads cannot copy the same value, then increment and then overwrite each other's updates. First of all, and second of all, whatever value gets written here, get updated to, that will be written back to main memory, right? So the next thread, the second thread, will see it. Now let's try to run this example again and see the difference. Now you can see the second thread reaches a total count of 2 million. Let's try to run it again and see that it reaches that consistently. Now you see both threads reach 2 million. And now you can see the second thread reaches it again, 2 million. So here is a fine example of how you can fix these data visibility problems using synchronized blocks. Java synchronized blocks also come with a happens before guarantee. And I have covered the happens before guarantee in a separate video. And if you check out the description below this video, you can find a link to it. So I won't get into too much detail about the happens before guarantee here, but I will still quickly just sum up what it is about. Now, the CPU and the Java virtual machine and the Java compiler as well, they are allowed to reorder the instructions of your code if they think that reordering the instructions will make the code execute faster. However, the compiler and the CPU can only make this determination from its own perspective, meaning from a single-threaded perspective. So have a look at these cases here. We have a synchronized exchanger here called syncx, and it has a set method here with a synchronized block inside, and inside of that we increment the count, which is the number of objects that have been exchanged or set, and here we just simply set the object to point to the object passed here as parameter. Now we're guaranteed that when the thread that calls set enters this block, that the count variable is read in from main memory, and actually this .obj is also written from main memory, but since it is overwritten just after, it doesn't really matter. However, when the thread calling set exits this synchronized blocks, we are guaranteed that the values of both count and object or obj will be written back to main memory. Now imagine that the Java virtual machine or the compiler or the CPU reorders the instructions, so the execution becomes as scheduled or sketched here on these two examples here on the right. In the first reordering example, the instruction this.count++ has been moved up above the synchronized block, so outside the synchronized block, and that means that this instruction is no longer covered by the synchronized block's visibility guarantees. More specifically, this means that we no longer have a guarantee that the thread calling set will refresh the value of count from main memory before incrementing it, and thus we don't know if we are losing some increments made by other threads. However, we do have a guarantee that once the thread exits the synchronized block here, that it will write whatever value that this.count has back to main memory, because even though it's accessed outside of the synchronized block, it is still visible to the thread that exits the synchronized block here, so it will still get synchronized back to main memory. However, as long as the thread doesn't properly refresh it from main memory, we can no longer trust the value of the count variable. In the second reordering example, the this.count instruction has been moved outside and below the synchronized block. And semantically, it looks like this code is still doing the same thing because these two instructions are independent of each other. They do not depend on the result of each other. However, now with the this.count instruction, count++ instruction down here, this instruction is now no longer guaranteed to be written back to main memory. We don't know when it will be written back. We do know, however, that whatever thread calls set will refresh all of the visible variables from main memory by the time it enters the synchronized block here. So both the value of count and obj will be refreshed from main memory. However, we do not know if the incremented value here will get written back to main memory or not. As you can see, instruction reordering may break the visibility guarantee of Java synchronized blocks, and that is why synchronized blocks come with a happens before guarantee, which puts some restrictions on what kind of instruction reorderings are allowed around synchronized blocks in Java. For the finer details, I have to refer you to my Java happens before video, and you can find a link to that in the description below this video. The Java synchronized block construct has a few limitations. First of all, only one thread can enter a synchronized block at a time. And there are some situations in which this limitation can be annoying. For instance, maybe you only wanted one thread to be able to write to a certain object at a time, but you would like to have multiple threads be able to read the values at the same time, as long as there's not another thread writing at the same time. And you cannot do this with just a synchronized block. However, you can use some of the read-write logs that are part of the Java util concurrent package to achieve that effect. The second limitation here is that there's no guarantee about the sequence in which waiting threads gets access to the synchronized block. And that means that if you have two threads that are waiting, and then one gets access and the other one has to keep waiting, and then another thread comes and gets enqueued waiting to get into the thread, so you have two waiting threads again, and then there's no guarantee that the first thread that has waited the longest time is then actually allowed in the next time. This is normally referred to as fairness. And because the Java synchronized block construct does not guarantee fairness, you risk what is called starvation. However, there are implementations of locks in the Java util concurrent package which provide such fairness guarantees, and you can use them instead if you want to achieve absolute fairness of the waiting threads. Entering and exiting synchronized blocks incurs a small performance overhead on your application. How big this performance overhead is depends on the situation. In situations where a thread tries to enter a synchronized block and that synchronized block is not already occupied or locked by another thread, then this performance overhead is quite low and you shouldn't worry about it. However, in situations where, for instance, a thread 2 is trying to access a synchronized block where another thread is already executing inside, then thread 2 gets blocked. And this incurs a higher overhead for thread 2 than it did for the first thread entering the synchronized block. And on top of the performance overhead associated with being locked and having to wait and being notified later on, the thread, of course, also loses all the time that it has to wait until the thread, the first thread here, has finished executing inside of this synchronized block. One final thing to notice about synchronized blocks in Java is that they can only block threads that are running within the same virtual machine. So if you have an application that is running on a cluster of machines, a cluster of virtual machines, then a thread entering a synchronized block in virtual machine 1 will of course never be able to block a thread that is entering a synchronized block in virtual machine 2. If you need such cross virtual machine locking, you will need to use another mechanism, either design one yourself or use, for instance, a database which also has locking capabilities, or find some open source tool that provides that functionality. That's all for this video about the Java synchronized keyword and synchronized blocks in Java. Remember to check out the description below the video for a link to a textual version of this tutorial, as well as links to other related tutorials. If you liked this video, please hit the like button, and if you want to see more videos like this, please subscribe to my YouTube channel.